All right, guys, good afternoon. I hope you're all good and you can hear me. All right, guys, good afternoon. I hope you're all good and you can hear me. All right, guys, good afternoon. Right. Okay, was getting some feedback there. Sorry about that. Um, so today we're on our third lesson. No, not third, fourth lesson. And yeah, I think it's been a great journey so far. Having revised quadratic number patterns, and then we looked at some varying questions, how questions are asked at exam level. We linked the quadratic number pattern with the linear number pattern, right? And then we also derived a general formula for the linear number pattern. So those are the few things that you should remember at this stage. So what we're going to do today, before we go into well, there's only one sequence left, and that's the geometric. So before we go into the geometric sequence and the geometric series, respectively, we've got to just fill up some gaps. And these, as you can see on your screen, we got to talk about sigma notation, and we've got to discuss logarithms as well, or logs, what is known as logs. We'll see if time permits. These are fairly new concepts. Last year in grade 11, you only did things like the quadratic formulas. That's one thing that was new in your algebra. But sigma notation, it's a new symbol that you're gonna be introduced to. And as I said, excuse me, it is very important that you pay attention to the symbols that we use in mathematics and what they mean. So we will start right there with the basic thing, what the word sigma means. And you'll see this as well. I mean, you've seen it already with trigonometry. You were introduced to letters, Greek letters like theta, alpha, etc., delta, and so forth. Now, that is basically the routine in mathematics. We often take Greek letters and we use that as symbol. But I must say, we actually do this with meaning. We do this with meaning. The word sigma actually means sum in Greek. So the symbol is this. So the symbol is like this. And you see this, it's just the letter sigma. All right. But the meaning, it's not just sigma, it means the sum of, so you are adding something. So what are you adding? All right. So it's going to be very important that we understand what this means. So let's say I've got the sum of a series denoted by K, TK. And then you will see oftentimes there will be something written at the bottom here. We will not always use K. We can use I. We can even use N. We could use P, whatever letter. And then here you will notice we will often use N. It does not matter what letter is being used. The main important thing to understand here is that the general look of sigma notation is that you're going to have the symbol sigma, which means sum of, and then you're going to have some letter which tells you the first value that you're going to start with. And this letter here at the bottom, excuse me, is an integer. Now you will notice I'm not saying a natural number. I'm saying an integer. What are integers? These are all your positive and negative numbers, all right? Loosely speaking, positive and negative whole numbers. So for example, a -3, a -2, a -1, 0, 1, 2, 3, and so on. So that's your set of integers. So when we classify something as an element rather of integers, oh, by the way, this little thing here, this little e here means an element of or belongs to. Okay. So I need you to really put meaning into these symbols when you read them. Don't just say K, E, Z, and that you must actually read them correctly in English to say where K is an element of the set of integers, or where the number k is a member of integers. Now, the n at the top here, again, it will not always be n. It could be a letter m, can be any letter. It could be an n plus 1 as well. This will always indicate the last value. All right. By the way, the reason we're doing this is so that we are able to express a series in a short form. You'll remember the last time we spoke about series, we were just writing them in long form where we said this plus this plus this plus this plus this, etc. So we use sigma notation as a shortcut or a short method, or more of a precise method of actually expressing a series. So that is why we are learning this, okay? Because sometimes we will not write a series in the way we've written them in the previous lesson. Sometimes we will write a series actually in terms of sigma notation. Okay, and as I said here, and you will see again, the use of brackets is quite crucial when it comes to sigma notation. And so somewhere in here, you will have an expression. Now, please take note. These are some of the things that there's going to be things I say that are very, very important, but I may not write. This expression must be in terms of K. ITO means in terms of. So if you don't see a K in the expression, it means the expression does not depend on K, okay? But typically, an expression will depend on K, and I think we're actually going to just spend time on sigma notation in this lesson. We might have to do logs in another lesson. So this is very, very important, and I'm going to kind of give you an illustration. So what I'm trying to say, this is what I'm trying to say. We can actually see these two expressions as equivalent. Remember from Thursday's lesson, this here means the sum of a series with n terms. But this is quite vague. It kind of doesn't tell us where to start. It just tells us we got to stop at n. There are n terms. So sigma notation is more precise in that it doesn't just tell us the sum of n terms, but this is what it says. This means sum of the series. Now here the series is well defined. How is the series defined? The series is defined by this general term tk. So this means the sum of the series tk, starting from the position k equals to 1 in this case. Sometimes we could say k equals to 0. So we could even go on to say k is equal to -2. All right. Hence, I pointed out that k must be an integer. So this, when you see this in sigma form, it actually says the sum of the series tk. Tk is the general formula for the series. Could be arithmetic or geometric. From k equals to 1 to n. N being the last position, the last term in that series. Okay, so let us just, for now, so that this is not overwhelming, let us just play around sigma notation. Let's see. Suppose we've got a question that says evaluate, and evaluate so let's do 2k minus 1. So what are we evaluating here? We are evaluating a series, because we have established from the previous lesson that in a series we are adding up terms, right? So we are evaluating the series expressed by the expression 2k minus 1. And take note that this expression indeed is in terms of k, the letter that is being used at the bottom of our sigma sign. We are doing this from number 1 from k equals to 1. Remember, your k is an integer. So we're going to start substituting integers from 1 up to 10. As you can see, that is our n value, or that's where we stop. So this literally means, so here's the literal meaning of this whole thing. When you see an expression like this, it means, watch this, 2 in the place of k, I'm going to put a 1. Now I'm adding. This is just my first term, right? So let's just do this. I'm adding because sigma means sum of. So I'm adding, then I'll substitute k equals to 2. And I'm going to keep adding up until 10. That is number 3. And then I'll keep adding. And because I'm a lazy mathematician, I will just do this and stop at 10. Like that. And then, of course, you can do this from memory, or you can do this using your calculator. I told you I'm going to teach you how to use the calculator. Now, those who have this calculator, it should have the sigma sign. It's here. It's right here. And then, oops, let me just do this. And so what you could do then is you could just, so everything that is in yellow will work with the shift button, this shift button, and everything that is in red will work with the alpha button. Okay, I hope you see that. So now, because I want to access the sigma sign, I will actually do this. That. And of course, because the calculator has been programmed to use X, okay? You'll never get a different letter, but we have K in our case. And so we said 2K plus 1. So I'm going to say 2X minus 1. Sorry, we said 2K minus 1. And then I'll just navigate through these arrows. We're summing up to 10. We're starting at 1. And then, as you can see, the calculator does this for me in just one quick step. I know there's 100. If you had to do this manually, you would obviously have to now figure out what this thing, you'd figure out what this thing is here. Okay, this is 2 times 1 minus 1, so that's just a 1. And then what you are also doing is you will have, I'm going to show you another way to do it, by the way. And then 2 times 2 is a 4 minus 1, that is a 3. So your next term is a 3, right? And then you have 6 minus 1, which is a 5. Okay, which is a 5. And then what you will realize here is that, wait a minute, I'm probably just adding odd numbers here, the first 10 odd numbers that are positive. So I'm sure you can see that surely the next term must be a 7. And then after a 7, you must get a 9. 1, 2, 3, 4, 5. 5, 6, 7. And then we gotta get 8. We gotta get 9. And then we're gonna get 10. That's gonna be our last 10. So these are the numbers that you're actually adding up. These are the numbers that you're actually adding up. So you could then add these manually in your calculator: 1 plus 3 plus 5 plus 7 plus 9. Now, that's the one kind of, I don't know if I should say the long way or the hard way to go about it. There is a quick way you could go about it. The quick way to go about it is to actually use the formula for Sn. If you remember what we discussed in a previous lesson, you will recall. Okay, so here you're going to add manually, and me trusting the maths, I'm not going to do the manual addition. I'm just going to write 100 here, believing that the calculator is in good health. So I'll just write 100. Now, if you do not have a calculator that has this function, then obviously I would suggest that instead of just writing this all out like this, like in this step here, Just want to show you how to do this nice and easy. Instead of just writing it in, writing this whole step here, the step that I'm highlighting in yellow, what you could do is to perhaps just work out the first 3 or 4 terms. And by the time you've worked out the first 3 or 4 terms, you should see that you are dealing with an arithmetic series. And in our previous lesson, we found a formula for actually calculating the sum of an arithmetic series up to n terms. So here you would notice, oh, okay, I'm dealing with an arithmetic series and the difference is 2. A being the first term is 1, and I'm just adding 10 terms here. So you could just go, well, S10 is equal to, and then you go n over 2, which is 10 over 2, into 2a, 2 times 1, plus n minus 1, which is basically 10 minus 1 times d, which is a 2. You could do this, and then you punch this whole thing in your calculator. N is 10 divided by 2, 2 times 1, plus n minus 1, which is 10 minus 1, times d, did I say 2? And then we close off the brackets, and just like that, we still get our 100. So you will then say this is equals to 100. So quick recap. You see something like this, and you go like, oh my word, do they really expect me to write the sum up to n 10 terms? Do I have to substitute every k value? No, you don't have to. What you can simply do is, one, if your calculator is advanced like the one I'm having, which I actually don't suggest because I know they're against the sum. Some examiners don't like this calculator. But then you could then just write it like this as in the yellow step, and then you write down your final answer. Which is 100, right, through this calculator. Alternatively, what you can do is, I'm going to show you in red now, you can write this step. After writing this step, you get to substitute into the sum formula. And of course, you got to just show your substitutions, because you might just get a mark for substitution and formula, and then you get for an answer. This here might just be 1 mark for expanding, okay? As I said, you do not have to expand right through. You can just expand up to the first 3 terms. For those of you who prefer using this formula that deals with the last term, you could have also gone S10 is equal to 10 over 2 into a, which is a 1, plus, excuse me, the last term is a 19, like that. And then, of course, this should give us the same thing. I'll leave it up to you to actually figure this one out. I mean, that's a nice, easy 100, because you got to have 10 over 2, which is a 5. You multiplying that by 20, it gives you the 100. So that's that. Of course, here you would have worked out the last term. So maybe let me write it down here. This is then an alternative. You could have gone 135, 1 plus 3 plus 5 plus up to, and then you write your last term as 19. And then in that way, you are more than welcome to use this formula here. And otherwise, you could use this. Any of the formulas really could work out. The bottom line is you do not have to rewrite the entire substitution from 1 up to 10. You actually need to show us that you do understand the relationship between sigma notation and the summation, the SN formulas, which we have discussed. Okay, so I hope you catch that part. What we're going to do now is we're going to take another example. And I just want to show you that it's not always going to start at 1, okay? Let's take another example. And then after taking maybe 2 more examples, we're going to have a look at some laws, some rules pertaining to sigma notation. And these rules are useful if you know them. They can help you really get away with some long questions or tough questions. Okay, so let's take the second example. If you missed it in the first one, let's see if the second example can find you. All right. So again, the question is standard. We have to evaluate. So evaluate the following. Okay, what are we evaluating in this case? The first one here, we've got, let's use the letter P here. P is equal to 3. And I have 2P. Let's maybe use a 5. 5P plus 4. So I'm looking for the sum of an expression 5P plus 4, where P starts at 3 and then end up to 10. Now, if we expand this, and I'm doing this example deliberately so that I can share a key principle with you here. If we were to literally expand, watch, this is what would happen. I would have 5 times 3 plus 4 as my first term, and then my second term would be 5 times 4 plus another 4, and then plus my third term would be 5 times 5 plus a 4, and then my fourth term would be 5 times 6 plus a 4. I'm going to rewrite all of them so that you see something very important here. Okay, but remember, you're not expected to do this, but I need to show you something. Before I show you this rule, I need you to see it as I expand manually. So this is 5 times 8 plus 4, and then this is 5. Oops. The pluses that are in blue are basically to illustrate the meaning of sigma. What is in black is just me substituting into the expression. Now, I'm not going to work this out. We will use a formula for that. I've got a plus 4 there. What I would like us to do, and what I need you to take note of, is that when I count the number of terms here, I've got 1, 2, 3, 4, 5, 6, 7, 8. I actually have 8 terms and not 10 terms. So one of the common errors that students make, and this is what I don't want you to do, okay? I'm warning you in advance. You're never going to make this error if you have attended this lesson with me, please, okay? Don't always assume that just because the top number above the sigma sign is a 10, then we've got 10 terms. No, of course, that will still give us the last term. It will still give us the last term. 5 times 10 is a 50. We add a 4, it's 54. So for sure, the last term for this series is a 54, whereas the first term will be 15 plus a 4, which is a 19. So that we will have. But remember, when you calculate the sum, you're calculating the sum of n terms. So the key issue then here is, how many terms are you actually dealing with? Now, of course, in this case, it seemed a little bit easy to work out because we could expand this, but we need a strategy. We need a short way to do this, because imagine I said to you, the sum of 99 from P is equal to 5. It will take you time to figure that out. Now, if you notice, there is quite an interesting relationship that we can actually use to always find the total number of terms when we are given a series in sigma notation. So to find the total number of terms, let me write it in red. Or to find, to know, or to determine the number of terms, I must maybe say the total number of terms in a series expressed in sigma notation. Or maybe let me write like number of terms for a series expressed in sigma notation. We will use the following formula. Let's use n for the total number of terms we will then say n is equal to, you take the top number, you subtract the bottom number, and then you add a 1. Let's see if that is the case. We have calculated in yellow about 1, 2, 3, 4, 5, 6, 7, 8 terms. So let's see. If I do 10 and that is the top one, and I subtract the bottom one, which is a 3, that's 7, and I add a 1, indeed I get an 8, which means you are actually trying to work out here the sum of 8 terms, not 10 terms. Sum of 8 terms. And for that sum of 8 terms, we will then use the sum formula for an arithmetic series. I'm hoping this arithmetic, of course it should be. I mean, if we're going to get a 19 here, the second one is 24, eh? Yeah, 5 times 4 is a 20. We add a 4. That's a 24. And then let's look at what the third term will be. It will be 29. I don't know. Are we subtracting the same number here? It looks like it, because the difference between 19 and 24 is a 5. And so it is between a 24 and a 29. So we can actually find S8 and then go, again, it depends which formula you want to use, whether you want to go 8 over 2 times 2a, which is 2 times 19, plus n minus 1 times a d, which is 5. That's quite a long way. Or you want to go, well, since I know the last term, Sn will be 8 over 2 into a, the first term, plus the last term of this particular series. And then you just punch this in the calculator, and then you'll tell me what you get there. But I get something like a 292. So it's really up to you which one you want to use. If you don't want to work out the last term and just quickly work out the first 3 terms, of course, then this becomes the cool formula to use. But if you have worked out the last term and the first term of the sequence, then of course, that becomes another option to use. Otherwise, you can also go straight into your calculator if you have that silver thing. This is not the only way in which we can ask questions involving sigma notation. As I said, we can be quite sneaky, right, as examiners. So I'm going to do another example that is sort of in a form of an equation. So look at this. And this is kind of a solve for x question. Check this one. Solve for x if the following is true. And here we are using the letter M. And then we have in here an expression 3m minus 2. And we are told this is equal to 1,150. So what we've got here is obviously a sum of a series. Of course, it's a series, but we don't know how many terms we are adding up. Okay, which means that formula for that has Sn in terms of the last term will not work, because we don't know the last term. We cannot know the last term if we don't know the number of terms we are dealing with. Okay, and we know that we don't really know the number of terms because, watch, to find the total number of terms, we must go top, which is x, minus bottom, which is a 4, and we must add 1 to that. Okay, so this simplifies to, watch this, n is x minus 3. We have 2 unknowns. We don't know what n is. We don't know what x is. Okay, so remember, in this instance, n is actually the total number of terms, and x is just the last position in the sigma expression. Okay, the last value of r, actually, of m, sorry. This x is actually the last value, the last integer we're going to substitute when we start at 4. And we don't know what that integer is. We are required to calculate that integer. Now, to do that, we have to recall the relationship that is there between sigma notation and the summation of any typical series. And how we're going to do this? Well, in this case, I'm just going to try and figure out the first three terms so I can find out whether this is arithmetic, if it is truly arithmetic. And if it is arithmetic, what is my first term and what is my constant difference? When I've got that, then I will be in a good position to solve this. So let's do that. 3 times 4 minus 2 is my first term. My second term will be 3 times 5. Remember, m is an integer, so we go up in ones. And then I'm just going to stop here where I substitute a 6. 3 times 6 minus 2. And I'll just indicate that this goes on and on. We don't know up to what. Then I'll just quickly simplify. 12 minus a 2 is a 10. And then 15 minus a 2 is a 13. 16. Is it a 13? Yes. And then 3 times 6 is an 18. We got to subtract a 2. That is a 16. Then I see now clearly that there is a constant difference of 3. So I know that I am dealing with a sum Sn, which is n over 2 because I am trying to find n here. And then I'll have to use this formula. I know my first term is a 10 plus I'm solving for n. And the constant difference is that. I actually know what Sn is. It is that 1,150. So let me indicate that. So what I can actually do here, I can equate that 1,150 to this entire thing. And then you know what I usually do. I'm going to take the 1150 and double it up to avoid fractions. So that will give me 2,300. So I've got n into, then I'm just going to clean up quickly here. That's 20 plus 3n minus a 3. And then we can just add some like terms there. 20 minus 3 is a 17. And then that's a 3n. This is 2,300 or 2,300. Then we're going to close it off now by using the quadratic formula because we do anticipate a quadratic equation here. Let's just try and write this nicely. Okay, so this will then be so what do I have now? So now I'll have a quadratic equation. 2,300 is equal to 17n plus, watch this, 3n squared. So this is a quadratic formula. I will work on the right-hand side. And then this is minus 2,300. So 0 is equal to that. Okay, then, as I said, just avoid wasting time and trying to factorize and all that. You're going to be vulnerable to making mistakes. So I would suggest you just go straight into your quadratic formula here. A standard procedure, we're going to use brackets whether we have positive or negative numbers. So that's b squared minus 4 times 3 times a negative 2,300. And then this is over 2 times 3. Then you're going to weigh this whole thing into your calculator, and then you're going to get two nice values. The first one will be, I'm getting a 25, and then the second one will be a fraction, which is 92 over 3. But we know n has to be a natural, so this solution is not applicable. So n is 25. And again, we see students stopping here because they'll be like, oh yeah, I'm done. But you are not done. Look at the box in yellow. Look at the original question. The original question said you must solve for x. You have solved for n. The box in yellow shows you the relationship between n and x. So you got to substitute the n back into that yellow, so and have an equation that reads 25 is equal to x minus a 3. And then you solve for x. So x becomes 25 plus a 3, and that is 28. So the actual value of x is a 28. Does this mean we have 28 terms? No, we have actually established that we are dealing with 25 terms. Here, you were just simply finding the value of x in an unknown equation. All right, guys, I want to pause here before I do the reverse and just check in if there's any question on the floor. If there isn't any, I will gracefully continue. You can just raise your hand there, or you can unmute and ask. None. Okay, so let's continue then. We don't have a question so far. Now, what we're going to do, we're going to do the reverse. As I said, we typically do the following in mathematics, okay? It's like you're on a road trip. We show you how to move from point A to B. But then if you know how to move from point A to B, you'll always then be required to know your way backwards, okay? So that's the basic thing, the structure, frame of work that we use in our teaching. So now that you know how to express, or rather how to evaluate a series given sigma notation, the reverse would be, okay, don't worry about the calculator. Kimi, don't worry much about the calculator. As I said, not everyone has the silver calculator. So what I would suggest is follow this basic method of actually expanding and figuring out whether you are dealing with geometric or arithmetic, and then finding your A and the constant difference, and then you substitute into the summation formula, this one here, the Sn, okay? Using the calculator directly sometimes might cost you marks because they may want to see you using the formula, substituting into the formula. I was just showing you a quicker way to do it there. All right. So let's do the reverse. Let's do the reverse. Still on sigma notation, okay? I don't know what example number this is. Why is the fraction not applicable? Okay, that's another question there coming up. Well, the fraction is NA because when we deal with number patterns, N must be a natural number. N must be a natural number. So natural numbers are numbers that are actually counting numbers. So counting, typically living things, 1, 2, 3, etc. And surely if you kept counting in that set of natural numbers, you're not going to find the number 92 over 3. You're never going to have something comma something in the set of natural numbers. So that is why we discard this 92 over 3. Okay. Right. Oh, okay. There's another hand. Bulali, yes. Go for it.
Yes, I was going to ask if we're ever going to be asked to calculate the value of m.
Let me just go back here. In other words, this starting position.
Yes, sir.
Is that what you're asking? Ooh, yeah, you're making me think actually of asking a question like that. But I've not seen that. I've barely seen that in the past papers. I think in case it is asked, I mean, you gotta think consecutively now. If they say m equals to I, maybe that will be asked in further studies. I'm sorry, I've not seen it in the scope of grade 12 mathematics. I've not seen it there. So I'll also send the examination guidelines for this year, because the examination guidelines will always tell us actually what to expect in the exam. So I'll have a look at that. But even the CAPS document, which I have checked, does not actually bring this. It does not require you to know how to calculate the bottom value. So At this stage, I think we're pretty much safe. Is this Takuv? You've got a question as well.
Sir, I wanted to ask how many marks would a question like this be?
Okay, so let's see. For expanding such that you get A and D, this could be plus minus 1, so it could be 1 mark or 2 marks. And then for equating this to the correct formula, you will get that. And you'll also have a mark for substitution here. Sometimes they will, as I said, it's always good to show your standard form, so they will do that. And then for both solutions here, they will do that. And then for actually solving for X, you will get a mark there. So what are we looking at here? 2 for about 7 marks. So I'll say 6 to 7 marks in this case, the solve for X part. All right. It could reduce to a 5 as well if the examiner sees other steps as routine. Okay. Right. Everyone happy? Shall we move on to the next example? Right. Okay. There's a comment there to say usually 5 marks. Okay. We're gonna do the reverse part. Okay. So here, as I said, can you work backwards now? So the question will go right. Write the following in sigma notation. So here's the series. I've got a -3, a -7. Okay, so I'm just kind of subtracting here. And this goes on and on. Take note up to a -123. Okay, so we want to rewrite this or write this thing sort of in sigma notation, right? So what we need to note is, let's just recap. When you've got sigma notation, you need a general term, let's use K, and you need a starting value, and you need an ending value, let's say N. Remember, TK is an expression in terms of K, the small letter here, all right? So that means we need to actually first find an expression for this whole thing. So we're gonna check, it does appear to be arithmetic. So let's just confirm. There are negative numbers, and as I said, this is always a trap, okay? So you wanna go -7, and you're gonna go subtract a -3. Okay, and then by doing so, we're gonna get a -4 here, and a -11 minus a -7 will give us a -4 as well. Okay, so clearly, this is truly arithmetic because we do have a constant difference, or T2 minus T1 is equivalent to T3 minus T2. Okay, now we go to our general formula for the arithmetic series, A plus N minus 1 times D. In case you missed this, that's what it is. So A here is a -3, and then this is gonna be general. Somebody's muted there. Okay, let's mute them. Okay, and then we've got a -4 here. This is -3. This is -4n, and that's a +4. So our general term really in this case is -4n plus a 1. Whether you want to write it as 1 minus 4n or minus 4n plus 1, it's immaterial for me. Right, so that's the general term. Now what we want to do is, so we have sorted this out, right? We have sorted that out. What we need to find then is, okay, where are we stopping with this? Where are we stopping? So I hope you notice that you actually have the last term given here. And there's a principle I shared with you last time, and I said you can always equate the last term to the nth term. So we can actually go now, negative 123 is equal to negative 4n plus 1. All right. And then this will become what? A negative 124, I suppose. And then we got to divide by a negative 4 both sides. So n is equal to 31. All right. And of course, in our case, we're going to start at 1 as far as the sigma notation is concerned. So therefore, this thing can actually be written as follows. So you can say now, okay, maybe let's write it somewhere here at the bottom. So for my final answer, I can say, well, the series -3, -7, -11, -15 up to a -23 can be written as the sum of the expression negative 4n plus 1. Nope, I can't use n here, hey? We want to try and avoid confusion, actually, because you got n in the general term and all that. So, guys, if you're going to pick a letter K, then let's use K here. If you pick the letter I, then you do the same thing there. So that is how we will reverse this process. Okay. It's all about finding the general term. That's your first thing that you're going to do. There's a bit of marks there. As I said, showing all your working, showing how you got to the answer is always golden in this mathematics thing. So if you can always do that, I think you'll stand a good chance to actually nail this. So this is the reverse part where you have to work backwards. You have to know both. You have to know how to evaluate an expression in sigma notation, but you also need to know how to take an entire series and rewrite it in sigma notation. There are nice, interesting, novel questions, and I think I'll just put up a document of past papers in the WhatsApp group so that you just go over this and see if you can actually do a sigma notation. Okay, I do see a hand. Kumvana. Yes.
Sir, I wanted to ask, does sigma notation also apply to the quadratic sequence?
Yeah, look, as I said, in CAPS, we don't do the quadratic series. It is there is a formula for that. I mean, though, if you're going to carry on with maths in university, you will come across that, you will see it. If there's anyone who takes further studies, you will also see that when you do things like mathematical induction. So it is there, but it is not within the scope of our curriculum. So you don't have to worry about it. It's only going to be asked in the context of the arithmetic and the geometric number pattern. Okay, or sorry, geometric series, not number pattern. So you're only going to get it in one of the two, either geometric or arithmetic. And we have not done the geometric yet, of course. I just wanted you to understand how the sigma notation works before we get to the geometric. I'll introduce that in our next lesson. Okay.
Okay, thank you.
Cool. Is that Uhone? You also have a question?
Yes, sir. I'm sorry, but I'm a bit confused with the second part. Would it be wrong if I use the top minus bottom plus 1 method?
Okay, so now the question is, what would be your bottom in that case? Well, what would be your bottom?
Okay.
Yeah, I don't think you have to worry about that in this case. You are doing the reverse. So in the reverse, you are literally just dealing with the series they have given you. And typically, you're working from what? Term number 1, term number 2, term number 3, and so forth. So you don't have to worry about the top minus bottom. There are instances where it becomes useful. I mean, you've seen in the previous example that that's where we had to use it. But in this case, because you really started with the first term that was given, and you were actually trying to find out up to what are you adding? We didn't really have to worry about that. You were given the last term as well. Okay. Right. Any other question? No one? All right, guys. So what I'll do is I will get this uploaded on the YouTube as well. And then, as I said, I will post a document. It's just a combination of past papers. But the nice thing about that document is that it is grouped according to sections. So the questions are grouped according to topics. You will have questions on number patterns. You'll have questions on functions, etc. So your focus for now will be on number patterns. And I want you to just try questions that are dealing with the sigma notation, but in the context of the arithmetic series, okay? If you see something that's geometric, if you have done geometric at school already, then it's fine. You can give it a try. But for those who have been following and you have not done the geometric series as yet, you can leave it out for now until we have covered the geometric series, okay? So I'll stop here for today. I think it's going to be a bit too much if we add logarithms right away. So we'll do logs in the next section, and then we do the geometric, because the geometric series does require some knowledge of logs, especially when we solve for n, or for when the unknown is in the exponential. So we're going to do a bit of logs before we go to the geometric. Okay, so yeah, see you guys next week, Sunday again. And then please stay tuned in the WhatsApp group for any updates, okay, regarding notes and past papers for you to stay on track. All right, all good.
Oh, sir.
Yes, we've got Mr. Slep, go for it.
Yes, sir. So we're done for the week.
Yeah, so look, I'll just send further communication regarding weekly sessions, okay?
Oh, okay.
Yes, I'll do that. Are you in the group, Slepe?
Yes, yes.
Okay, fantastic. Yeah, then you'll just see the communication. I'll just communicate stuff there. All right. Just guys, stay tuned for that revision pack, and just keep up with actually the different types of questions that can be asked. The more past papers you do, that's the better your chances of doing exceptionally well in your final exam. So we'll keep sending a lot more throughout the year. Just make sure you do your honest part. I usually say this, okay? To be on par with your maths, you need to at least commit or dedicate 3 hours per week, not per day, per week, okay, of just self-practice. This is excluding your teaching and learning at school. This is even excluding a session like this one. You need that 3 hours of personal time with mathematics. It's up to you how you want to spread it. You want to do it in 20 minutes intervals. You want to do it in 30 minutes intervals. It's really up to you, but you have 7 days a week or 6 days, because you got to rest, right? You need 1 day to at least rest. So you got 6 days. See how you can spread this 3 hours over 6 days. Of course, for those of you with a quest, with the love to actually want to do exceptionally well, then you have to spend more time, okay? Just like Ronaldo, who practices when other players have gone home so that he is best. It's like that in maths. If you want to really be the best, you got to give it more time than the average time of 3 hours, okay? But we'll keep sharing some of these tips along the way. So yeah, cheers, we'll see you. What if they include variables in the sequence to find the sigma notation? How do you do this? Let's go over that. Let's chat about that in the WhatsApp group. I'll also open a window. If you actually have a question in Lindy that has something like that, you're more than welcome to send it through as well. We'll tackle it for you. So cheers, guys. We'll chat with you on the WhatsApp group shortly.